Maxwell's theories, the electromagnetic theory of light. In the preceding chapter, we have seen that when a condenser in series with a self-inductance and resistance is charged and allowed to discharge, the current obtained if the resistance is not too large will be oscillatory in character. In this arrangement of apparatus, we have a mechanism that serves as the source of electric waves. In 1865, Maxwell predicted by mathematical reasoning based on some experiments of Faraday that variable currents in a conductor produce electric waves in space, that these electric waves travel with the velocity of light, and that light itself consists of electric waves of extremely short wavelengths. While direct experimental verification of this theory by the actual discovery of electric waves did not come during Maxwell's lifetime, Maxwell yet showed that his predictions were strongly supported by many of the known facts about electricity and light. Without the aid of mathematics, it is difficult to follow the steps of Maxwell's reasoning, so that the discussion here given will undoubtedly appear to the reader to be inconclusive. In the next chapter, we hope to remedy this defect of the theoretical discussion by a description of the actual experimental demonstration of the chief propositions of Maxwell's theory. In the derivation of his theory, Maxwell makes use of the two facts about the relation of electricity to magnetism that we have given in chapter 3. Namely, 1. An electric current in a conductor produces a magnetic field in the neighborhood of the conductor, and 2. A variable magnetic field in the neighborhood of a conductor produces an electromotive force in the conductor. To these two well-known experimental facts, Maxwell adds a third proposition in the form of an assumption, which has been called the displacement assumption. The displacement assumption. This assumption is an attempt on the part of Maxwell to give expression to the idea of Faraday that when a condenser is charged, the condition of things is not completely described by saying that a positive charge is given to one plate and a negative charge to the other plate of the condenser. Faraday showed that something takes place in the medium between the plates, and Maxwell makes the assumption that the action in the medium partakes somewhat of the nature of an electric current, although the medium is an insulating substance. It is difficult to determine just how Maxwell imagined this action to take place, and different writers have employed different mechanisms in the description of the current that Maxwell supposed to exist in the insulators. One way of representing his idea is to suppose that the insulating medium, whether a solid, liquid, or gaseous dielectric, or even empty space, is made up of small parts, and to suppose that the electricity in these small parts of the insulator may flow freely in the small parts but cannot flow from one part to the next. If we call these small parts molecules, we may describe the current in the insulating medium as the act of polarizing the molecules. That is, for example, when the left-hand plate of the condenser in figure 19 is charged positively, the positive electricity added to this plate attracts the negative electricity and repels the positive electricity of the neighboring molecules, so that the part of each molecule near the plate becomes negative and the distant part becomes positive. Molecules in this condition are said to be polarized. The layer of molecules so polarized acts on the next layer and produces a similar polarization, so that in turn the molecules throughout the medium between the plates become polarized. It is seen that this general transfer of positive electricity to the right and negative electricity to the left in the molecules would have an effect similar to an electric current flowing from the positive plate to the negative through the insulator. Maxwell called this general transfer of electricity in the dielectric a displacement current. During the charging of the condenser, the displacement current is in the same direction as the current in the conducting parts of the circuit, so that the displacement current may be said to complete the conduction current. During the discharge of the condenser, the dielectric loses its polarity and according to Maxwell's view, gives rise to a displacement current in the dielectric. In this case also, the displacement current completes the conduction current, which is now flowing away from the positive plate of the condenser. It has been stated above that the displacement current partakes of the nature of an electric current. The displacement current differs from the ordinary current in that there is within the molecules nothing corresponding to ordinary resistance, so that none of the energy of the displacement current is converted into heat. The displacement current also differs from the conduction current in that the displacement current, under a given applied electromotive force, sets up a restoring force in the dielectric, which, like the reaction of a compressed spring, soon becomes large enough to equalize the electromotive force and stop the current, whereas the conduction current in a circuit that is wholly conductive continues to flow as long as the electromotive force is applied to the circuit. These are the differences between the displacement current and the ordinary current. On the other hand, according to Maxwell's theory, the displacement current is exactly like an ordinary electric current in respect to its relation to the magnetic field. We may thus add to the two propositions stated earlier the proposition 3. In the case of a circuit not entirely closed by conducting parts, the current in the conducting parts is completed by a displacement current through the dielectric. This displacement current produces a magnetic field in its neighborhood, and a variable magnetic field in a dielectric produces displacement currents in the dielectric. Our electric waves. In Maxwell's treatise, the propositions I, 2, and 3 are discussed quantitatively, with the result that he obtains a number of quantitative relations about light and electricity. However, without such a mathematical discussion, we may still see how the facts assumed to be correct in proposition 3 lead to the idea of electric waves in the dielectric. For this purpose, let us suppose that we have two conducting bodies of the form shown in Fig 20. A and B are two metallic rods with a small spark gap between them. Suppose now that A is charged with electricity of one sign and B with electricity of the other sign, and suppose the charges are gradually increased until a spark passes between them. If the resistance is not too large, the current that flows will be oscillatory because the rods have electrostatic capacity and self-inductance. The two metallic rods here pictured constitute an electric oscillator. According to Maxwell's theory, the oscillatory currents in the oscillator will be completed by displacement currents in surrounding space. A part of this displacement current takes place along the black loops in the direction of the arrows from one end of the oscillator around to the other. The displacement loops are really sections of a sheet, such as would be obtained if we rotated the figure about the oscillator as an axis. These displacement currents in the sheet will reverse their direction when the current in the oscillator reverses, and are accompanied by a magnetic field of which a single line is shown encircling the displacement sheet. The magnetic field produced by the displacement current in the shaded region, being oscillatory in character, will induce displacement currents in a portion of the medium farther out from the oscillator, and the latter current will lag somewhat behind the former. Thus, a sheet corresponding to the shaded region will sustain a displacement current oscillating with the period of the oscillator. The unshaded region farther out will sustain similar oscillations a little later, so that we have the condition of things that exists in a wave motion traveling with a finite velocity, namely a series of disturbances first in one direction, then in the opposite direction, taking place all over a closed surface and traveling outward from the source. The electric waves. A masterly mathematical treatment by Maxwell of this idea of an electric displacement in dielectric media led not only to great progress in the knowledge of electromagnetism, but also to a complete revision of theories as to the nature of light, so that now all the phenomena of optics are describable in terms of Maxwell's electric waves. From his theory, Maxwell deduced the following facts in regard to electric waves. 1. The electric wave in the dielectric consists of a displacement current in one direction with a magnetic force at right angles to it, both of these quantities being in the wave front, that is to say, at right angles to the direction of propagation of the wave, see Fig. 21. Thus, electric waves, like light waves, are transverse waves. 2. The velocity of propagation of the electric waves in a non-magnetic insulating medium is a divided by the square root of k, where a is the ratio of the CGS electromagnetic unit of quantity to the CGS electrostatic unit of quantity, and k the dielectric constant of the medium. In empty space, by definition, k is unity, and the ratio A was known from older experiments to be the velocity of light, 3 times 10 to the power of 10 centimeters per second. Whence the velocity of the electric waves in free space is identical with the velocity of light, which is 3 10 to the power of 10 centimeters, or about 186,000 miles, 7 times around the Earth in 1 second. 3. In an insulating medium other than free space, for example in glass or paraffin, it is seen from the preceding section that the velocity of the electric waves is v equals a divided by the square root of k equals v squared divided by the square root of k, in which v squared is the velocity of waves in free space, and v the velocity of the waves in a dielectric of dielectric constant k, whence v squared divided by v equals the square root of k. 4. All good conductors are opaque to electric waves, all good insulators are transparent to electric waves, and semiconductors like wood and stone are semi-transparent. Metallic surfaces are practically perfect reflectors of electric waves. The electromagnetic theory of light. Among these several properties of electric waves, the properties stated in 1 and 2 are identically true of electric waves and light, while the properties enumerated in 3 and 4 have also met with very useful application to light as well as to longer electric waves. Thus, Maxwell came to the conclusion that light waves are electric waves of short wave length. This theory is now generally accepted. It is interesting to note on this theory how light can be produced. We have seen how electric waves may be produced by oscillating electric currents in a circuit of the form shown in Fig 20. Now, if we suppose the oscillator of Fig 20 to be made smaller and smaller, the capacity and inductance will both be decreased, and the time of oscillation is thereby decreased. If then we think of the oscillator as possessing atomic dimensions, the period of oscillation approaches that of light. It is, however, not necessary to think of an actual electric discharge taking place between the atoms of our atomic oscillator, because the rapid vibratory motion of a single charged particle or electron back and forth would have the same effect as an electric discharge between particles and would produce electric waves of which the period, for a particular size and velocity of the vibrating particle, would be the period of light of some particular color. Let us turn next to the experimental demonstration of the existence of the electrical waves predicted by Maxwell. This did not come during Maxwell's lifetime. In fact, 22 years elapsed between Maxwell's remarkably clear presentation of the theory and Hertz's brilliant confirmation of it. That is to say, the index of refraction of a medium for electric waves is equal to the square root of the dielectric constant of the medium.